We have with us Professor Motaz Atala, University of Birmingham, who will be talking in advances in research in Middle East.
Hello, everyone. Today I'll be giving a quick overview about how 3D printing can be used to enable topological design. And that is applied mainly to metamaterials and structures for different applications. My name is Mu'taz Atala. I'm a professor at the University of Birmingham School of Metallurgy and Materials. I'll probably start with the introduction about topology. So topology as a topic is a study of geometrical properties and their spatial relations. And it's unaffected by the continuous change of shapes or size of figures. So it's a mathematical field, but people have been trying to look into more of an the engineering side of topology, to see how when we change the relationship between these points when they are available in space, they might achieve an improvement in their behavior and their response to different stimuli. As you know, for a number of years, people have been using topology optimization as an expression in additive manufacturing. So topology optimization is basically a mathematical framework that can be applied on many software packages currently, where the material layout can be optimized within a certain space by applying certain boundary conditions, whether these are mechanical loading boundary conditions, whether we are putting constraints on thermal, heat transfer, fluid flow, and so on, with an optimum goal of maximizing the performance of that component. One of the components that people saw for a number of years and different additive manufacturing conferences was the famous Airbus bracket, which was previously made out of steel, was heavy, was around 0.9 kilogram. The shape itself was not optimized for mechanical loading, so the maximum stress it saw was around 840 megapascal as well. But then by using topology optimization and the science of topology as a framework to redesign the component, making it out of titanium, the shape was redesigned, printed by additive manufacturing, achieving a component which is almost half a kilogram less than the original shape. And because of the use of struts and the use of that kind of biological design, the loads were distributed more homogeneously, with the stresses approximately being halved into the stresses that were in the original component. So you can see that massive weight reduction, massive load reduction as well, maximum load reduction was achieved by topology optimization. That is probably the commonest example, but what I'm going to talk about today is how topology and the science of, or the art of controlling where the shape and where the components, where the material is in space, may improve the behavior of many other applications. So today I'll be giving just snapshots of different components. Different materials, like the ones available on the left-hand side, are commonly printed nowadays. Aluminum alloys, nickel superalloys, titanium alloys, nickel titanium shape memory alloys, soft magnetic materials, materials with low coefficient of thermal expansion, like Invar, for instance, refractory metals that are used in high temperature application. But when we put these in an additive manufacturing context, we get new or totally new applications that are probably the first time we see them. The first one I'll be talking about is radio frequency and microwave guides, which can be optimized and printed using additive manufacturing, achieving superb performance that can be very difficult to achieve using conventional manufacturing. Then I'll talk about nickel-based superalloys, which have been printed to maximize heat efficiency and heat transfer properties of heat pipes for thermal management in different applications. Then I'll talk about their application as well in catalysis, in components which require a high surface area to volume in order to enable the application of high temperature loads into these components. From there, I'll talk about titanium implants and how titanium implants can be redesigned to allow us to deliver drugs by having cavities within those shapes. I'll talk about, in titanium alloys, also about sonic crystals, which are shapes that have certain acoustic behavior, also by optimizing the topology. And then I'll talk about lattices and stents as a way of optimizing shapes and topology. I'll talk about porous structures and their applications in medical implants. I'll talk about negative Poisson ratio materials and their application in shock absorption. And beyond that, I'll talk a little bit about magnetic shielding and low CTE structures and materials. And then finally, I'll talk about high temperature refractories, which are applied in nuclear fusion applications, and also about X-ray collimation. Let me start by an exciting application which comes from the space sector. I showed you this shape, the so-called sonic crystals. Sonic crystals demonstrate an interesting arrangement of material in space. And that arrangement of material is used to dampen the sound waves. So as a sound wave goes through the sonic crystals, you can see that only a small amount of that big amplitude of a sound wave will survive, and then the majority of, or big part of the amplitude is going to be reflected backwards. So by designing the size of the ball, the distance between the ball, you can actually tune that structure to reduce the load and to block a certain sound frequency, provided that you know the frequency and you know exactly what you want to block. So this was a part of a program we did with the European Space Agency looking into the use of these sonic crystals for noise reductions in launch pads, which are known to be very noisy. And through this and through using additive manufacturing, you'll be able to create different complex shapes that can be used to tune the frequency and to tune the noise damping behavior and allow us to achieve a much quieter operating structures in that case. Let's move into another one, which is 3D printing for telecoms. This shape you see in front of you is a microwave radio frequency guide. And those guides typically can be made by casting, but then if you want to make a very complex shape similar to this one with the spherical domes, then additive manufacturing comes as a very interesting process that you can use for this. We've been printing these parts out of aluminum alloys, which are well established and well defined in additive manufacturing. And the good news is that the shape that you print by additive manufacturing is literally spot on the required frequency, compared, for instance, with metal casting, where you can see more significant variations in the tuning of the frequency of that shape. More importantly, if you want to improve the level of the quality of the signal, you can apply surface finishing using grinding techniques to clean the internal surfaces and cavities, allowing us to achieve a quality value, the so-called Q value, which is very, very close in its quality compared with the ideal material, which is in this case is designed of pure aluminium with a surface finish of 1 micron RA. Printing it, of course, using a high-strength aluminium alloys like this one can allow you even to make the thickness much smaller, and as a result also achieve an additional benefit when it comes to weight reduction as well. Moving on into another application, one of the projects we are currently involved in at the University of Birmingham involves 3D printing or looking into quantum or so-called gravity sensors. These gravity sensors, they operate using a technology called the cold atom technology, where they generate the material into, or they can generate a form of material in a very low temperature. And then when that happens, you become, the material or it becomes very sensitive to gravity fluctuations. So if you put it on a satellite, for instance, you will find out there's oil somewhere in Canada, there is some tungsten or uranium in Chile. You will know exactly where there are some strong gravity fields at different locations in the material. So the current shape of those gravity sensors, they look like a mechanoset put together with a lot of components. And what we have been doing is that we're trying to make a nice packaging for them. But one of the key factors we want to consider is the use of magnetic shielding to prevent any interference from any surrounding magnetic fields. Now, if you're trying to measure fluctuations in the Earth's gravity field, so you want to also eliminate any potential for interference from the surrounding. But you also want this to be light. You also want it to be optimized, whereby you can have multi-wall shielding. And this cannot be achieved by, again, by additive manufacturing, by conventional manufacturing. So when you use additive manufacturing and you combine it with something like multi-physics COMSOL simulation, you start to generate designs that enable you to even achieve a more enhanced way of shielding and more enhanced way of generating those magnetic shields. I'll move into another application, also onto how we tailor material, or how we tailor the topology of the material and where we put it. We did a while ago a project with Rolls-Royce looking into efficient cooling, and that was through the use of what's known as heat pipes. These heat pipes are typically made out of copper with powders inside, and they achieve cooling through the so-called wicking behavior, where the liquid just goes through the height and allows for heat to be lost through the component. Instead, what we tried to do was that we basically printed them using SLM. We generated a structure with a very high surface area, as you can see on those the teeth you see in front of you. Each one of them is around the 100 microns, let's say, and in terms of their height, around 1 millimeter in height, and they surround the shape. They are very rough, but being rough was also very good, because if you compare the response of these structures we printed and how quickly the liquid will climb in terms of the wicking behavior, you can see that the copper reference had a response time of around 7 seconds or so to reach to around 40 behavior, 40 height in terms of the wicking. Whereas the structures made by additive manufacturing using simple notches or simple grooves or simple shapes that we printed similar to those ones was able to get into roughly the same height but a much shorter time. So in fact, playing with the topology, playing with the design, we're able to achieve a more efficient cooling and much rapid thermal response from these shapes and structures. Normal shapes, normal materials, if you apply load into them, they become short and fat. Whereas this material, if you apply load into it, it becomes short and it gets smaller, actually. That's because of the design of the material will get those struts and links to move inside and close together. We did a project with the STL, the UK's Ministry of Defence, looking into the application of this technology into armor, especially if an armor is being hit by this material. Basically, the material will move towards blocking it and it will densify to prevent it from further progressing inside the material. So this is where, if you want to think about it, if you put the same amount of material as a simple block compared with putting the same amount of material but only as an auxetic shape, you will achieve a much more significant behavior from an armor point of view, and the prevention of the material progression when it's hit during impact. Talking more about topology and how topology can be interestingly computed and controlled. This is one of our current projects which looks into 3D printing of stents. And stents, as you know, as we all get old, we end up having what's known as stenosis. So our arteries start to become narrower. And usually the cardiologist has to interfere with something we call stent to open the arteries and allow for the blood flow to flow normally inside the body. The problem is that in many cases they will find multiple stenosis sites. So they will start to add like 1 or 2 or 3 stents as in order to open up the full artery. What we said is, why do we try to make why don't we try to customize the stent by doing the topology customization in this case for the patient? So the stent, its design itself, exactly like people have been doing in medical implants, becomes customized to the patient, becomes tailored by or customized according to the lesion itself, the anatomy of the patient. And from there, we start to print those stents, and we've been since then printing them, looking into how they behave and doing a lot of testing inside a vessel that is used to simulate blood flow inside them. And so far, this has been filed for a patent, because we're looking into how this can potentially be the next thing into additive manufacturing of stents, so that we can control, or we actually create customized stents in the same way that people create customized medical implants. Lattice structures and the uniform arrangement. And this is the example of the graded lattice, where the porosity in the middle is different from the porosity at the edge. When we looked into their mechanical loading, we found that the material that has the uniform lattice usually has that 45-degree densification behavior. So and then eventually it breaks at that direction. These are position maps measured by digital image correlation. Whereas if you are making a material that has the density is changed from the outside to the inside, the part itself starts to squeeze and change its geometry and closing upon itself, similar to how those auxetic materials behave. But then looking into these materials, one of the things we found was that we can, by playing with the design, we can play with the degree of porosity, we can even generate control in the elastic modulus, achieving very low levels of elastic modulus, approximately 5 gigapascal, which is even and lower, which is close to the density or even lower the density of the bones, which can enable us to tailor the parts of the medical implants from the outside to the inside in order to generate, to mimic the mechanical behavior of what we do in those stents, in those medical implants, compared with the bone. Last case study, looking into medical implants one more time. So typically when you make a medical implant, they are typically dense, solid, but we decided to apply or to create cavities inside those medical implants, similar to this screw. So when you create a cavity inside, that cavity then can be filled with medicine, whether this medicine is an antibiotic or anti-inflammatory drug. You create cavities and small holes on the sides or on the 45 MV and on the bottom. And then through using that system, you will end up generating a medical implant that can generate. One of the challenges, though, that we have seen was how to create the right size of the hole. And that involved significant optimization, really, to be able to reach there. Because the problem in additive manufacturing is that if you want to make a 0.5 mil hole, you are unlikely to get 0.5 mil hole. You're probably going to get something like 150 mil hole. So you did a lot of optimization to be able to achieve the right dimensions of the holes in order to allow for the drug to leak from inside from different locations. And eventually we looked into the scheme of what we want to produce. This is an example of a hip stem of a hip implant. And as you can see, by having that cavity inside with those holes coming out of it, you will end up generating a drug delivering implant that can be used to treat certain infections locally rather than taking the antibiotic, let's say, through the bloodstream. So this is where we are. So I take this now as a chance for us to try to announce one of the newest programs that we have started in Birmingham, which I'm greatly excited about. We've started recently an initiative on a Center for Doctoral Training in Topological Design, basically teaching people about the science and art of topology, linking that into a number of themes, looking into topological design in mechanical, thermal, and vibration engineering, looking into the application in quantum physics and technology, like the case study I've given you, looking into its application in electromagnetism and photonics. Didn't cover that one, but that's another way when you can use topological design to optimize things related to optics, for instance, or related to electromagnetism. Topological design in health and life sciences, I've given an example about that in the STENS case study. Application in soft matter and chemistry, which still evolving. I haven't covered that one, but this is one of the ones we're working on. And then looking into the math, computation, and data sciences of topological design. And then last but not least, focusing primarily in manufacturing and 3D printing using topological design. We are very excited about this initiative. We created, since then, an ecosystem that links people who work in theory with the so-called enabling technologies and looking into applications in the themes that I mentioned and covered a minute ago. That's all what I wanted to say. I'm very thankful for Objectify for the invitation, and I'll be very happy to get your questions by email or on Twitter if you are interested in our work. These are the people who did the work. I would like to thank them and thank you all. Thank you.
Thank you for the amazing session. It was really insightful. Hope you have learned a lot from this session.